Light has been arriving at Earth tonight from a source that no longer exists in any form we would recognize. Radiation that has been traveling through space for approximately 13 billion years. This is not light from a distant star or a faraway galaxy, but something far older, something that began its journey before any stars or galaxies existed anywhere in the universe. The radiation fills all of space, coming from every direction equally. A faint glow that permeates the cosmos and reaches every corner of the observable universe, including the small blue planet where you are listening tonight. This ancient light is called the cosmic microwave background, and it represents the oldest electromagnetic radiation that we can detect with our instruments or observe in any way. The light began its journey when the universe was only 380,000 years old, a tiny fraction of its current age of nearly 14 billion years. Since then, it has been traveling through expanding space, crossing distances that the human mind struggles to comprehend, finally arriving here after the longest journey any light can take. You are listening to The Drowsy Astronaut, and tonight we are exploring this ancient light, the oldest thing we can observe. The remnant glow of the early universe still reaching us across billions of years of cosmic time. If you enjoy these calm journeys through the cosmos, consider leaving a comment about where you are listening from tonight, and perhaps a like if you find this helpful for rest. The light we explore tonight has been patient, traveling for eons without rushing, and we will explore it with similar patience, letting the story unfold slowly as the night continues. The journey of this light spans almost the entire history of the universe, a voyage that began when the cosmos was young and hot and filled with glowing plasma rather than the stars and galaxies we see today. When this light first began traveling, Earth did not exist, the sun did not exist, and even the atoms that would eventually form our planet had not yet been assembled into their current arrangements. The light has been traveling since before anything familiar existed, crossing the void while the universe slowly built itself into the structure we observe around us tonight. 13 billion years is difficult to grasp because nothing in human experience provides a useful comparison for timescales of this magnitude, stretching beyond comprehension. If the entire history of human civilization were compressed into a single second, the journey of this light would span roughly 400,000 years of equivalent time. The light was already ancient beyond measure when the first single-celled organisms appeared in Earth's oceans. And it continued traveling for billions of years more as life evolved and eventually produced minds capable of detecting its faint arrival. The patience of this light is absolute, traveling at the fastest speed anything can travel, yet still requiring billions of years to complete its journey across the expanding universe. Light moves at approximately 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second of ordinary time. Yet even at this tremendous speed, crossing the observable universe requires time measured in billions of years, the cosmos being vast beyond easy description or casual understanding. Every second, more of this ancient light arrives at Earth. Photons that have been traveling since before any of the familiar landmarks of the cosmos existed in their current forms. The light arriving tonight is not the same light that arrived yesterday, though it comes from the same source and carries the same information about conditions in the early universe. Tomorrow, Light that is currently still traveling will arrive, completing journeys that began alongside the light we detect tonight, but taking slightly different paths through the expanding cosmos. The light comes from every direction equally, not concentrated in any particular region of the sky, but spread uniformly across the entire celestial sphere surrounding our position. This uniformity reveals something fundamental about the source, which was not a single point or a collection of objects, but rather the entire universe itself, glowing in every direction at once. The light comes from everywhere because it was emitted from everywhere, the whole cosmos serving as the source rather than any particular location within it. Looking up at the night sky on a dark, clear evening, this ancient light is present but invisible to human eyes, its wavelength too long for our visual system to detect directly. The radiation exists in the microwave portion of the electromagnetic spectrum, between radio waves and infrared light, invisible but detectable with appropriate instruments designed for this purpose. The faint glow surrounds us always, day and night, filling the space through which we move, even though we cannot see it without technological assistance. The detection of this light requires sensitive radio receivers capable of measuring extremely faint signals against the noise of the equipment itself and the environment. The temperature of the radiation is only about 3 degrees above absolute zero, making it extraordinarily cold and correspondingly faint compared to most sources astronomers observe regularly. Yet it fills all of space, and its total energy content is substantial when considered across the entire volume of the observable universe surrounding our position. The cosmic microwave background represents a kind of fossil, a preserved record of conditions in the early universe, frozen in light that has been traveling ever since those conditions existed. Just as fossils in rock preserve information about ancient life on Earth, this radiation preserves information about the ancient cosmos before structure had formed. The light carries a message from the past, encoded in its temperature, its spectrum, and the subtle patterns of variation that sophisticated instruments have revealed over decades of careful observation. This fossil light tells us that the universe was once very different from what we observe today, filled with hot plasma rather than cold, empty space, punctuated by galaxies. The transition from that early state to the current state involved many processes unfolding over billions of years. But the light was released at a specific moment and has preserved information about that moment ever since. We receive this information tonight, billions of years after the fact, because light travels at finite speed and distant events take time to become visible from our location. The journey of this light through the cosmos has not been entirely uneventful, as the expansion of space itself has affected the radiation during its long voyage between there and here. Space has been stretching throughout the history of the universe, carrying galaxies apart from each other, and also stretching the wavelength of light traveling through the expanding medium. The light arriving tonight has been stretched significantly during its journey, transformed from its original form into the microwave radiation we detect today. The stretching of the light reveals itself in the temperature we measure, far colder than the original emission, because expansion has drained energy from the radiation over billions of years. When the light began its journey, the universe was hot enough to glow visibly, bright enough that no darkness existed anywhere, because everything was emitting light in every direction equally. The current faint microwave glow is the cooled remnant of that original brightness, dimmed and stretched by the expansion of the cosmos itself over cosmic time. The light continues arriving from every direction, a constant reminder of the cosmic history that preceded everything familiar in the night sky visible to unaided eyes tonight. The stars we see are young compared to this light, having formed billions of years after the radiation began its journey through the darkness. The galaxies that contain those stars are also young by comparison, structures that assembled from matter that was once part of the glowing plasma that released this ancient light. Understanding this light requires understanding the universe from which it emerged, a cosmos so different from our own that it seems almost like a different place entirely, despite being the same universe at an earlier time. That early universe, hot and dense and filled with light, is the subject we turn to next. The source from which this ancient radiation has been traveling across the billions of years, separating that epoch from tonight. The light that fills space tonight began in conditions that no longer exist anywhere in the observable universe. A sea of hot plasma where light and matter were intertwined in ways that physics no longer permits. That early state and the processes that ended it released this radiation on its long journey through expanding space toward eventual detection by instruments that would not exist for billions of years after. The light first began traveling toward where they would someday be constructed. The universe that released this ancient light was utterly unlike the cosmos we observe today. A place without stars or galaxies or planets or any of the structures that define the astronomical landscape we study with our telescopes. Instead of distinct objects separated by vast empty spaces, the early universe was filled uniformly with hot, glowing material that occupied every location and left no room for darkness or emptiness anywhere at all. This was a cosmos made of light and plasma, a continuous glow extending in every direction without boundary or interruption. The temperature of this early universe was approximately 3,000 degrees, hot enough that all matter existed as plasma rather than the neutral atoms that make up most things today. Plasma is a state where electrons are not bound to atomic nuclei but roam freely through the material, creating a sea of charged particles that interacts strongly with light passing through it. In this state, the universe was opaque, meaning light could not travel freely, but was constantly scattered by the abundant free electrons filling all of space. This opacity meant that the early universe had no transparency, no ability for light to travel from one place to another without being deflected or absorbed along the way. A photon of light in this early plasma would travel only a short distance before encountering an electron and bouncing off in a new direction randomly. The light was trapped, scattered continuously, unable to propagate freely through the dense sea of charged particles that filled the cosmos uniformly from edge to edge. The temperature of 3,000 degrees produced a characteristic color for this glowing plasma, an orange-white hue similar to the color of a heated metal or the glow of an incandescent light bulb filament. The entire universe glowed with this warm color, every location emitting light of this temperature, in every direction equally without variation or structure. There were no shadows because there was nothing to cast them, no darkness because every point in space was a source of light just like every other point. Being inside this universe would have been like being inside a uniformly glowing fog. Surrounded by light coming from every direction, with no way to see any distance, because the opacity prevented distant objects from being visible. Not that there were distant objects to see, since the universe had not yet formed any structures that might be distinguished from the background glow surrounding them uniformly. The cosmos was smooth and featureless, a continuous plasma without the clumps and voids that would later define cosmic geography. The matter in this plasma consisted almost entirely of hydrogen and helium, the two lightest elements, present in a ratio of about 3:1 by mass that had been established in the first few minutes after the universe began expanding. Heavier elements did not yet exist because no stars had formed to create them through the nuclear fusion processes that occur in stellar cores. The chemistry of this early universe was simple, just two elements in plasma form, uniformly distributed throughout the entire cosmic volume. The light that filled this plasma was in equilibrium with the matter, meaning the radiation had the same temperature as the plasma, and the two were continuously exchanging energy through the interactions between photons and charged particles. This equilibrium produced what physicists call a black body spectrum, a very specific distribution of light across different wavelengths that depends only on the temperature and nothing else. The spectrum of the cosmic microwave background preserves this black body form, evidence of the equilibrium that once existed in the early universe. The uniformity of this early universe was remarkable, with the temperature and density being essentially identical at every location throughout the entire cosmic volume accessible to our observations today. This smoothness is actually somewhat puzzling, as we shall explore later. But for now, we simply note that the early universe was extraordinarily homogeneous compared to the lumpy structured cosmos we observe around us today. The plasma was the same everywhere, glowing at the same temperature, containing the same mix of elements in the same state. Yet, this uniformity was not quite perfect, and the tiny departures from perfection would prove to be essential for everything that came later in cosmic history. The density of the plasma varied slightly from place to place, with some regions having perhaps 1 part in 100,000 more matter than average, while others had slightly less. These variations were tiny, almost unmeasurably small, but they would eventually grow under the influence of gravity to form all the structure we observe in the universe today. The universe in this state was young, only about 380,000 years old, a mere infant compared to its current age of nearly 14 billion years. This sounds like a long time by human standards, but it represents only about 1/30,000th of the universe's current age, a tiny fraction of cosmic history. The universe had been expanding and cooling since its beginning, and at this age, it had cooled enough that something important was about to happen, to change everything. The expansion of the universe was carrying every part of the plasma away from every other part, stretching space itself and causing the temperature to drop as the radiation was spread over ever larger volumes. This cooling had been going on since the beginning, and the temperature had dropped from unimaginably hot initial conditions to the 3,000 degrees that characterized this epoch. The cooling would continue, but something was about to interrupt the relationship between light and matter that had existed since the beginning. The plasma that filled the universe was about to undergo a transformation, a change of state that would alter the nature of the cosmos fundamentally and release the light that would travel for billions of years, to reach us tonight. This transformation would convert the plasma into neutral atoms, clear the cosmic fog, and allow light to travel freely for the first time in the history of the universe. The opaque, glowing universe was about to become transparent and dark. The moment when this happened, when the universe cleared and light was set free, is the moment that produced the cosmic microwave background that we detect in every direction today. This moment occurred at a specific time in cosmic history, about 380,000 years after the beginning, and it happened everywhere in the universe at approximately the same time. The light that was released in this moment is what has been traveling ever since, filling space with the faint glow that our instruments detect as the oldest observable radiation. The physics of this transition involved the capture of free electrons by protons to form neutral hydrogen atoms, a process that became favorable once the temperature dropped below a critical threshold. While the universe was hotter than 3,000 degrees, electrons had too much energy to remain bound to protons and would be knocked free by collisions with energetic photons. Below this temperature, the electrons could finally settle into stable orbits around protons, forming neutral atoms that no longer scattered light efficiently. This process of electron capture is called recombination, though the name is slightly misleading because the electrons and protons had never been combined before, having been separate since the universe was very young and very hot. The term stuck despite this historical inaccuracy, and recombination is now the standard name for the epoch when atoms first formed in cosmic history. The process was rapid once it began, transforming the cosmic plasma into neutral gas over a relatively short period of cosmic time. The transformation from plasma to neutral atoms changed the relationship between light and matter fundamentally, ending the opacity that had characterized the universe since its earliest moments. Neutral atoms are nearly transparent to most wavelengths of light, allowing radiation to pass through without the constant scattering that occurred when free electrons were abundant. The universe became clear, and the light that had been trapped in the plasma was suddenly free to travel without obstruction. The moment when atoms formed and light was freed represents one of the most significant transitions in cosmic history, a change that transformed the nature of the universe fundamentally and permanently. Before this moment, the universe was opaque, filled with glowing plasma that scattered light continuously and prevented radiation from traveling freely across cosmic distances. After this moment, the universe was transparent, allowing light to propagate without interruption through space that had suddenly become clear after hundreds of thousands of years of fog. The transition occurred when the temperature of the universe dropped below approximately 3,000 degrees, cool enough that electrons could finally remain bound to protons rather than being knocked free by energetic collisions. At higher temperatures, photons of light carried enough energy to ionize atoms, stripping electrons away as quickly as they could attach to nuclei and maintaining the plasma state. Below this critical temperature, atoms became stable, and the free electrons that had been scattering light disappeared into bound states around atomic nuclei. The process happened relatively quickly, once conditions permitted, transforming the entire observable universe from opaque plasma to transparent gas over a period of perhaps 100,000 years. This sounds like a long time, but it represents a rapid transition compared to the age of the universe and the timescales over which most cosmic changes occur. The fog lifted across the entire cosmos within this period, clearing everywhere at approximately the same time, as expansion brought temperatures below the critical threshold. As the electrons were captured by protons, the free electron density dropped precipitously, and with it, dropped the probability that a photon of light would scatter before traveling any particular distance through the medium. The mean free path of photons, the average distance they could travel between scattering events, increased dramatically as neutral atoms replaced the plasma. Within a cosmically brief period, the mean free path became larger than the observable universe, meaning photons could now travel forever without scattering. The light that had been trapped in the plasma was suddenly released, free to travel in whatever direction it happened to be moving when the last scattering event occurred that would ever affect it. Each photon scattered one final time, off one final electron, then continued on a straight path through the suddenly transparent universe, traveling without further interaction until it eventually reached a detector or was absorbed by some intervening matter billions of years later. This final scattering event for each photon occurred at a specific time and place in the early universe, and the collection of all these final scattering events forms what astronomers call the surface of last scattering. This surface is not a physical object, but rather a conceptual boundary, the locations from which the cosmic microwave background photons were released toward our eventual position in the universe. When we observe the cosmic microwave background, we are looking at this surface, seeing the universe as it appeared at the moment of last scattering. The surface of last scattering surrounds us in every direction at the same distance. Since the release of light happened everywhere at the same cosmic time, and we observe it from our position at the center of our observable universe. This creates a spherical shell of last scattering around our location, with the cosmic microwave background coming from every direction at the same cosmic distance and representing the same cosmic epoch. The uniformity of the background across the sky reflects the uniformity of conditions at this surface. The light released in this moment carried information about the conditions at the surface of last scattering, encoding the temperature, density, and other properties of the plasma at the instant before it became transparent neutral gas. This information has been preserved in the radiation during its journey, carried across billions of years of cosmic time to reach instruments capable of extracting and interpreting the encoded data. The cosmic microwave background is thus a message from the past, a snapshot of the early universe preserved in traveling light. The temperature of the plasma at the moment of last scattering was approximately 3,000 degrees, and this temperature determined the color and spectrum of the light that was released into the newly transparent universe. The radiation had a characteristic blackbody spectrum corresponding to this temperature, with most of the energy at wavelengths in the near-infrared and visible portions of the electromagnetic spectrum. The universe glowed orange-white at this moment, though no eyes existed to observe the color directly. The moment of last scattering marked the end of what cosmologists sometimes call the dark ages of the universe, though this terminology can be confusing since the universe was actually bright before this transition and dark afterward. The term refers to the fact that after recombination, the universe contained no sources of light, the primordial glow having been released, and no stars yet having formed to provide new illumination. The cosmos was transparent but dark, filled with neutral gas and traveling radiation but no luminous objects. This dark period would last for hundreds of millions of years until the first stars formed and began illuminating the universe with newly generated light from nuclear fusion in their cores. During this time, the only light in the universe was the cosmic microwave background radiation traveling through the darkness, cooling and stretching as space expanded, but otherwise unchanged. The first stars eventually formed from the subtle density variations that had been present in the plasma before recombination. The physics of recombination can be understood through relatively straightforward atomic physics, involving the capture of electrons by protons to form hydrogen atoms in their ground state configuration. The process competes with photoionization, where photons break apart atoms by providing enough energy to free the bound electrons back into the plasma. Below the critical temperature, recombination wins this competition, and the neutral fraction increases until essentially all the free electrons have been captured. The transition was not perfectly sharp, occurring over a range of temperatures and cosmic times as the balance between recombination and ionization shifted gradually toward the neutral state. Some regions of the universe became neutral slightly earlier than others, depending on local conditions, though these variations were small compared to the overall homogeneity of the early universe. The surface of last scattering thus has a slight thickness, representing the range of times over which the transition occurred across the cosmic volume. The photons released at last scattering began their journeys in a universe very different from the one they would eventually reach after billions of years of travel through expanding space. The cosmos at this time contained no structures, no galaxies or stars or planets, just smoothly distributed neutral gas filling all of space uniformly. The slight density variations that existed would take billions of years to grow into the structures we observe today, seeded by tiny fluctuations but requiring cosmic time to develop. The direction each photon traveled was random, determined by the angle at which it scattered during its final interaction with an electron in the recombining plasma. Some photons headed toward where Earth would eventually form. Others headed in completely different directions toward other parts of the cosmos. The photons we detect tonight are those that happen to be traveling toward our location, a tiny fraction of the total radiation released at recombination, but still an enormous number, arriving continuously. The universe at the moment of last scattering was approximately 1,000 times smaller than it is today, with all the distances between points compressed by this factor compared to their current values. The cosmic microwave background photons have traveled across the entire expansion that has occurred since that time, their journey spanning the growth of the universe from this early compact state to its current vast dimensions. This expansion has profoundly affected the radiation during its journey. The light released at the moment of last scattering was not microwave radiation when it began its journey, but rather near infrared and visible light with a temperature of approximately 3,000 degrees. The transformation from that original warm glow to the cold microwave radiation we detect today occurred gradually during the journey. As the expansion of space stretched the wavelength of the traveling photons over billions of years of cosmic time, this stretching is the reason we call it the cosmic microwave background, rather than the cosmic visible light background. Space itself has been expanding since the universe began, carrying galaxies apart from each other and stretching everything within the cosmic volume, including the wavelengths of light traveling through the expanding medium. This expansion is not galaxies moving through space, but rather space itself growing, with the distance between any 2 points increasing over time as new space is created everywhere, uniformly. Light traveling through this expanding space experiences the stretching directly, its wavelength increasing in proportion to the expansion factor. When the cosmic microwave background was released, the universe was about 1,000 times smaller than it is today, meaning all distances were compressed by a factor of 1,000 compared to their current values. Since that time, space has expanded by this same factor, and the wavelength of the traveling light has been stretched by the same amount. Light that originally had a wavelength of about 1 micrometer now has a wavelength of about 1 millimeter, shifted from the visible and near-infrared into the microwave portion of the electromagnetic spectrum. This stretching of wavelength corresponds to a decrease in the energy carried by each photon, since the energy of light is inversely related to its wavelength through a fundamental relationship in quantum physics. The photons have been losing energy throughout their journey, drained by the expansion of space rather than by any collision or absorption event along the way. The cooling of the cosmic microwave background from 3,000 degrees to less than 3 degrees reflects this energy loss accumulated over billions of years. The current temperature of the cosmic microwave background is measured to be approximately 2.725 degrees above absolute zero, an extraordinarily cold value that reflects the enormous stretching the radiation has experienced during its journey. Absolute zero represents the lowest possible temperature, about minus 273 degrees on the common temperature scale, and the cosmic microwave background is only slightly warmer than this theoretical minimum. The universe has cooled by more than a factor of 1,000 since the radiation was released. This temperature corresponds to a characteristic wavelength of about 1 millimeter, squarely in the microwave portion of the electromagnetic spectrum, between radio waves and infrared radiation. Microwave radiation is invisible to human eyes, which are sensitive only to a narrow range of wavelengths in the visible spectrum, explaining why we cannot see the cosmic background directly, even though it fills all of space around us. Only with appropriate instruments can we detect this ancient light arriving from every direction continuously. The spectrum of the cosmic microwave background preserves the blackbody form it had at the moment of release, though shifted to lower temperature and longer wavelength by the expansion. A blackbody spectrum has a very specific shape, determined entirely by the temperature of the emitting object, and the cosmic microwave background matches this theoretical shape with extraordinary precision. The measurements confirm that the radiation truly originated in thermal equilibrium, exactly as the theory of the early universe predicts should have occurred. The stretching of light by cosmic expansion is called redshift because visible light becomes redder, shifting toward longer wavelengths as it is stretched by the expanding universe. The redshift of the cosmic microwave background is the largest we can observe, corresponding to the greatest distance and earliest time from which light can reach us across the cosmic void. No radiation from an earlier epoch can reach us because the universe was opaque before recombination, blocking our view of anything that might have come before. The expansion of the universe has continued since the cosmic microwave background was released, and it continues today, carrying galaxies apart and stretching any light traveling through the cosmic volume. The rate of expansion has changed over cosmic history, influenced by the matter, radiation, and dark energy that fill the universe. But expansion has never ceased, since the beginning. The cosmic microwave background continues to cool as space continues to expand around us. The factor of 1,000 by which the universe has expanded since the cosmic microwave background was released is called the redshift factor for this radiation, conventionally denoted as 1 plus Z, where Z is approximately 1,000 for the cosmic microwave background specifically. This redshift factor tells us how much the universe has expanded during the journey of the light, and equivalently, how much the wavelength has been stretched. Larger redshift values correspond to more distant and earlier sources. The journey of the light through expanding space was not instantaneous, but required billions of years to complete. Even though light travels at the maximum speed permitted by the laws of physics, the cosmic microwave background photons have been traveling for approximately 13.8 billion years, nearly the entire age of the universe, since they were released at the moment of recombination. Their journey has occupied almost all of cosmic history that we can observe. During this journey, the photons passed through space that was initially empty of any structure, but gradually developed galaxies, stars, and all the cosmic infrastructure we observe today. The light traveled through the dark ages when no stars existed, through the epoch of first star formation, through the assembly of galaxies and clusters, all while the universe expanded and cooled around the traveling radiation. The journey was a passage through cosmic history itself. The photons arriving tonight have traveled distances far larger than 13.8 billion light-years, despite the universe being only 13.8 billion years old, because the expansion of space has stretched the distances during the journey. The cosmic microwave background photons were emitted from locations that are now about 46 billion light-years away, carried to these remote distances by the expansion that has occurred since the light began traveling. The observable universe has grown around the journeying radiation. The expansion continues to affect the cosmic microwave background, even now, stretching the radiation very slightly with each passing moment, as space grows between every point and every other point. In the far future, the radiation will be even colder than it is today, stretched to even longer wavelengths and lower energies by the continuing expansion of the universe. This cooling will continue as long as the universe expands. The transformation of the cosmic microwave background from visible light to microwave radiation is thus not an artifact of any special process, but simply the result of the light traveling through expanding space for an enormous length of time. The same physics that stretches light from distant galaxies into redshifted observations stretches the cosmic background by an even larger factor because it has been traveling for longer. The stretching is the accumulated effect of cosmic expansion over nearly the entire age of the universe. The story of how this stretched, cooled radiation was first detected involves accidental discovery and gradual recognition. A tale that unfolds in the 1960s when two radio astronomers stumbled upon a signal they could not explain with any known source of interference or equipment malfunction. Their accidental discovery would confirm predictions that had been made decades earlier and would transform our understanding of cosmic history fundamentally and permanently. The discovery of the cosmic microwave background occurred in 1964 and 1965 at a research facility in Holmdel, New Jersey, where two radio astronomers were using a large horn-shaped antenna originally designed for satellite communication experiments rather than astronomical observations. Arno Penzias and Robert Wilson had been granted use of the antenna for radio astronomy work after its original purpose had been completed, and they were preparing it for observations of radio sources in the Milky Way galaxy. What they found instead would change the course of cosmology. The antenna was a remarkable instrument, about 20 feet long, with a distinctive horn shape, designed to minimize the detection of radiation from unwanted directions that might interfere with satellite signals. This careful design made the antenna unusually well suited for detecting faint, diffuse radiation coming from the entire sky, though this was not its intended purpose when it was constructed for Bell Telephone Laboratories. The researchers had access to one of the most sensitive radio receivers available at the time for their astronomical work. When Penzias and Wilson began their observations, they encountered a persistent noise in their instrument that they could not eliminate through any adjustment or modification of their equipment or observing procedures. The noise appeared as a faint hiss in the receiver, corresponding to a temperature of about 3.5 degrees above absolute zero, present in every observation, regardless of where the antenna was pointed or when the observation was made. The signal came from every direction equally. The researchers spent considerable time trying to identify and eliminate this annoying interference, convinced that it must represent some malfunction of their equipment or some local source of radio noise that they could track down and remove from their observations. They checked the electronics. They cooled the receiver to reduce thermal noise. They examined every component of the antenna system for possible sources of the mysterious signal. Nothing they tried made the noise go away. One possibility they investigated was contamination of the antenna by pigeon droppings, since the horn provided a sheltered location where pigeons had taken up residence and left their mark on the instrument's surface. The researchers carefully cleaned the antenna, removing what they politely called a white dielectric material from the interior surfaces, and evicted the pigeons that had made the horn their home. The noise level remained exactly the same after this cleaning operation. The signal showed no variation with time of day, time of year, or direction in the sky, behavior that ruled out most possible sources of terrestrial or astronomical interference that might explain the persistent hiss in their receiver. Solar radiation would vary with the sun's position, galactic sources would be stronger toward the Milky Way, and terrestrial interference would typically show some directional or temporal pattern. This signal was constant and isotropic, the same in every direction at every time. While Penzias and Wilson were struggling with their mysterious noise, a group of physicists at Princeton University was preparing to search for exactly the kind of radiation that the Bell Labs researchers had accidentally detected. Robert Dicke and his colleagues had realized that if the universe had begun in a hot, dense state, as the Big Bang theory suggested, the remnant radiation from that early epoch should still be detectable as a faint microwave glow, filling all of space. They were building their own detector to search for this predicted radiation. A mutual acquaintance connected the two groups, informing Penzias that the Princeton researchers might have an explanation for the mysterious noise that had been plaguing the Bell Labs observations. When the two groups communicated, it became clear that Penzias and Wilson had detected the cosmic microwave background that Dicke's team had been preparing to search for systematically. The accidental discovery had preceded the intentional search. The recognition that the mysterious noise was in fact the remnant radiation from the early universe transformed the observation from an instrumental nuisance into a discovery of fundamental cosmological importance. The temperature of about 3 degrees matched predictions that had been made years earlier by theorists who had calculated what the cooled remnant of the hot early universe should look like. The signal came from every direction because it originated from the entire universe glowing uniformly in its early hot state. The two groups published their results simultaneously in 1965 in the Astrophysical Journal, with Penzias and Wilson reporting the measurement and Dickey's group providing the cosmological interpretation that explained what the measurement meant for our understanding of the universe. The papers established the cosmic microwave background as an observed phenomenon and confirmed the Big Bang theory as the correct description of cosmic history over the steady-state alternative that some cosmologists had preferred. The discovery earned Penzias and Wilson the Nobel Prize in Physics in 1978, recognition of the profound importance of their accidental observation for our understanding of the cosmos. Robert Wilson later recalled that they had not set out to discover the cosmic microwave background and had not initially understood what they had found when the persistent noise appeared in their data. The significance emerged only through the connection with theoretical predictions. The temperature they measured, about 3.5 degrees, was slightly higher than the currently accepted value of about 2.7 degrees, reflecting the limitations of their measurement techniques and the difficulty of precisely calibrating such a faint signal. Later measurements with more sophisticated instruments would refine the value, but the original detection established the basic result that has been confirmed by decades of subsequent observation with ever greater precision. The discovery was remarkable partly because the radiation had been detectable for years before anyone recognized its significance. The technology having been available, but the theoretical motivation lacking to prompt a search. With hindsight, the cosmic microwave background could have been detected much earlier, but without the theoretical framework connecting it to the early universe, any detection would have been dismissed as unexplained noise. The discovery required both the observation and the interpretation. The horn antenna used for the discovery still stands at the Bell Labs site in New Jersey. Now a National Historic Landmark, recognizing its role in one of the most important discoveries of 20th century physics. The instrument that was designed for satellite communications became instead a tool for cosmology, detecting radiation from the edge of the observable universe, rather than signals from orbiting satellites. Its unexpected contribution to science far exceeded its planned purpose. The signal that Penzias and Wilson detected was extraordinarily faint, but extraordinarily important, revealing for the first time that the universe retains a detectable memory of its early hot state, preserved in radiation that has been cooling for billions of years. The discovery opened a new window on the early universe, allowing scientists to study conditions that existed long before any stars or galaxies formed, and long before any of the familiar features of the cosmos came into being. The temperature of the cosmic microwave background, so precisely measured by subsequent experiments, tells us about the current state of the universe and allows us to calculate backwards to determine what conditions were like when the radiation was first released. This temperature has become one of the fundamental parameters of cosmology, measured with extraordinary precision and revealing the properties of the universe itself. The temperature of the cosmic microwave background has been measured with remarkable precision by instruments both on the ground and in space, converging on a value of approximately 2.725 degrees above absolute zero, the coldest natural temperature we can measure anywhere in the observable universe. This temperature represents the current state of the radiation that has been cooling for nearly 14 billion years, stretched and dimmed by cosmic expansion from its original hot, bright state at the moment of release. The value tells us something fundamental about the cosmos itself. 2.725 degrees above absolute zero corresponds to approximately minus 270.4 degrees on the common Celsius temperature scale, colder than any place on Earth or any natural environment in the solar system. Absolute zero, the theoretical minimum temperature where all thermal motion ceases, is about minus 273 degrees Celsius, and the cosmic microwave background is only slightly warmer than this limit. The universe has cooled to within a few degrees of the coldest possible state. This temperature is not the temperature of empty space, in the sense that space itself has a temperature, but rather the temperature of the radiation that fills space uniformly in every direction. The cosmic microwave background represents a bath of photons filling the entire universe, and the temperature describes the energy and wavelength distribution of these photons according to the blackbody spectrum they have maintained since their release. Everything in the universe is bathed in this faint glow. The uniformity of this temperature across the sky is one of its most remarkable features, with the same value measured in every direction to extraordinary precision when certain known effects are accounted for in the analysis. The temperature varies by less than 1 part in 100,000 from one direction to another, an almost perfect uniformity that tells us the early universe was extraordinarily smooth and homogeneous. The variations that do exist, though tiny, are cosmologically important. Measuring such a faint and uniform signal required the development of specialized instruments capable of detecting microwave radiation with sensitivity far beyond what was available when Penzias and Wilson made their accidental discovery. The technology for precise cosmic microwave background measurements has advanced enormously over the decades, with each generation of instruments achieving better sensitivity, better resolution, and better control of systematic errors. The current measurements represent the culmination of this progress. The COBE satellite, launched in 1989, made the first space-based measurements of the cosmic microwave background spectrum, confirming that it matched a perfect blackbody to extraordinary precision. The spectrum measured by COBE was the most perfect blackbody ever observed, showing no deviations from the theoretical curve at any wavelength where measurements were made. This perfection confirmed that the radiation truly originated in the thermal equilibrium of the early universe. The blackbody nature of the spectrum means that the temperature completely characterizes the radiation, with all other properties determined by the single temperature value. A black body is an idealized object that absorbs all radiation falling on it and emits radiation with a specific spectrum determined only by its temperature. And the cosmic microwave background matches this ideal more closely than anything else we have ever measured. The early universe was an almost perfect black body. The temperature of 2.725 degrees corresponds to a characteristic wavelength of about 1 millimeter, placing the peak of the blackbody spectrum in the microwave portion of the electromagnetic spectrum. This wavelength is much longer than visible light, but much shorter than typical radio waves. Falling in a region of the spectrum that requires specialized detectors, different from either optical telescopes or radio receivers. The microwave technology used for measurements has heritage in both astronomical instruments and communication systems. The energy density of the cosmic microwave background can be calculated from its temperature using well-established physics, yielding a value of about 400 photons per cubic centimeter, filling all of space uniformly. This means that the space around you right now, wherever you are listening, contains about 400 cosmic microwave background photons in every cubic centimeter of volume. The photons are everywhere, passing through you and everything around you continuously. The total energy in the cosmic microwave background across the entire observable universe is enormous, despite the low energy of each individual photon and the low temperature of the radiation overall. When summed over the vast volume of the cosmos, the cosmic microwave background contains far more photons than all the stars and galaxies combined, outnumbering visible photons by a factor of more than 1 billion. The universe is flooded with this ancient light. The temperature of empty space, in the sense of the radiation filling space, has cosmological significance beyond simply characterizing the cosmic microwave background itself. Any object in space that is not producing its own heat will eventually cool to this temperature, reaching equilibrium with the ambient radiation bath that fills the cosmos. This temperature represents a kind of floor for cooling in the present-day universe. The precision of the temperature measurement has improved enormously since Penzias and Wilson's original observation of approximately 3.5 degrees, with the current value known to better than 1 part in 10,000 uncertainty. This precision allows cosmological calculations that depend on the temperature to be performed with corresponding accuracy, constraining models of the universe far more tightly than was possible with earlier, less precise measurements. The uniformity of the temperature across the sky tells us that the early universe was almost perfectly smooth, with matter and radiation distributed nearly uniformly throughout the cosmic volume. This smoothness is actually somewhat surprising from a theoretical perspective, requiring explanation through mechanisms that operated in the very early universe before recombination. The uniformity poses a puzzle that we will explore later in our journey tonight. The tiny departures from perfect uniformity that do exist in the cosmic microwave background temperature are actually more informative than the uniformity itself, encoding information about the conditions in the early universe that would determine the formation of all cosmic structure. These variations are only about 30 millionths of a degree from the average, barely detectable even with the most sensitive instruments. But they contain the seeds of everything. The cosmic microwave background temperature will continue to decrease as the universe expands, dropping ever closer to absolute zero over the billions of years still to come in cosmic history. The radiation that is now at 2.7 degrees will eventually cool to 1 degree, then to fractions of a degree, as space continues to stretch and the wavelength continues to lengthen. The cooling that has been ongoing for billions of years will continue indefinitely. The temperature of the cosmic microwave background connects us to the early universe in a direct and measurable way, providing a window into cosmic history that no other observation can match. The value we measure tonight is the cooled remnant of the hot beginning, carrying information about conditions that existed when the universe was less than 500,000 years old. This ancient temperature surrounds us in every direction. The cosmic microwave background is almost perfectly uniform across the sky, but not quite And the tiny deviations from uniformity that do exist represent some of the most important information encoded in this ancient light. These variations in temperature are extraordinarily small, only about 30 millionths of a degree from the average, barely detectable even with the most sensitive instruments we have ever built. Yet, these tiny fluctuations contain the seeds of all cosmic structure. The variations appear as slightly warmer and slightly cooler spots distributed across the microwave sky, a pattern of subtle differences overlaid on the otherwise uniform glow of ancient radiation reaching us from every direction. The warmer spots correspond to regions of the early universe that were slightly denser than average, where a bit more matter had accumulated in tiny primordial overdensities. The cooler spots correspond to regions that were slightly less dense than average. The temperature differences arise because photons escaping from denser regions had to climb out of deeper gravitational wells, losing energy in the process, and arriving at our detectors with slightly lower energy than photons from less dense regions. This gravitational redshift effect connects the temperature variations we observe to the density variations that existed in the early universe when the radiation was released. The temperature map is actually a density map of the primordial cosmos. The density variations encoded in the cosmic microwave background are the seeds from which all cosmic structure grew, the slight overdensities that would eventually collapse under gravity to form galaxies, clusters, and the cosmic web that organizes matter on the largest scales. Without these primordial variations, the universe would have remained perfectly smooth forever, with no galaxies, no stars, no planets, and no possibility of complexity arising anywhere. The tiny fluctuations made everything possible. The magnitude of the variations, about 1 part in 100,000 of the average temperature, tells us that the early universe was extraordinarily smooth, while still containing the minimal structure necessary for cosmic evolution to produce the lumpy universe we observe today. If the variations had been much smaller, gravitational collapse would have been too slow to form structures within the age of the universe. If they had been much larger, structure would have formed too quickly and too densely. The pattern of variations is not random, but contains statistical regularities that encode information about the physics of the early universe and the conditions under which the primordial fluctuations were generated. The angular scale of the variations, how large the spots appear on the sky, tells us about the geometry of the universe and the speed of sound in the early plasma. The relative amplitudes at different scales tell us about the composition of matter and energy. The detection of these tiny variations required instruments far more sensitive than those that initially discovered the cosmic microwave background itself, since the signal of interest is more than 100,000 times smaller than the average temperature being measured. The first detection came from the Kobe satellite in 1992, when the instrument team announced that they had found the predicted fluctuations at approximately the expected amplitude. The result was hailed as one of the most important discoveries in cosmology. George Smoot, the Kobe team leader who announced the detection of the fluctuations, described the result as looking at the face of God, expressing the profound significance of seeing the primordial structure from which everything we know emerged. The religious metaphor captured the sense of awe that many scientists felt upon seeing the first image of the early universe, the baby picture of the cosmos, before any of its familiar features had formed. The image was fuzzy but revolutionary. The COBE detection confirmed that the fluctuations existed at roughly the amplitude that cosmological theory had predicted, validating the standard model of cosmic structure formation that explained how the uniform early universe became the lumpy structured cosmos we observe today. The basic picture of gravitational amplification of primordial density perturbations was confirmed by the measurement, placing the theory on solid observational footing for the first time. The angular resolution of COBE was limited, showing only the largest scale fluctuations in the cosmic microwave background and averaging over smaller scale details that contained additional cosmological information. Subsequent missions would improve this resolution dramatically, revealing finer details in the primordial pattern and extracting more information about conditions in the early universe. Each generation of instruments saw more clearly. The variations we observe were imprinted by physical processes operating in the early universe, likely during a period of rapid expansion called inflation that occurred in the first tiny fraction of a second after the universe began. Inflation stretched quantum fluctuations in the very fabric of space to cosmic scales, creating the pattern of density variations that would eventually be revealed in the cosmic microwave background and in the distribution of galaxies. The tiny wobbles of quantum physics became the seeds of cosmic structure. The preservation of these variations in the cosmic microwave background for billions of years demonstrates the remarkable fidelity with which light can carry information across cosmic time and distance. The pattern imprinted at the moment of last scattering has survived the journey unchanged, allowing us to read the record of the early universe as clearly as if we were observing it directly. The light has been a faithful messenger. The variations in the cosmic microwave background have been mapped with increasing precision by successive generations of instruments, each revealing more detail in the primordial pattern and allowing more precise extraction of cosmological parameters. The WMAP satellite improved on COBE's resolution by more than an order of magnitude, and the Planck satellite improved further still. The maps have become our most detailed images of the early universe. The statistical analysis of these variations has become a sophisticated science, extracting from the pattern the values of fundamental cosmological parameters with percent-level precision. The age of the universe, the composition of matter and energy, the geometry of space, and other properties can be determined from careful measurement of how the temperature varies across the microwave sky. The cosmic microwave background has become a precision tool. The slightly warmer and cooler spots that pepper the cosmic microwave background map represent the most ancient structures we can observe. Older than any galaxy or star, older than atoms themselves in their current configurations. These primordial density variations are the earliest detectable features in the history of the universe. The first structures to emerge from the smooth beginning, and the ancestors of everything that exists today. The connection between these tiny temperature variations and the vast structures of the cosmic web is one of the most remarkable verifications in all of science, linking observations separated by billions of years of cosmic time through a coherent physical theory. The same physics that explains the variations in the cosmic microwave background also explains the distribution of galaxies, confirming our understanding of cosmic evolution across the entire history of structure formation. The mapping of the cosmic microwave background has progressed through successive generations of instruments, each more sensitive and precise than its predecessors, building an ever more detailed picture of the early universe preserved in ancient light. From the first detection of variations by COBE to the exquisite maps produced by the Planck satellite, the image of the primordial cosmos has sharpened progressively, revealing details invisible to earlier generations of observers and extracting information that was beyond reach with less capable instruments. COBE, the Cosmic Background Explorer, was launched by NASA in 1989 and operated until 1993, making the first precision measurements of the cosmic microwave background from space, where interference from Earth's atmosphere could be eliminated. The satellite carried instruments to measure the spectrum of the radiation, confirming its perfect blackbody form, and to map the temperature variations across the sky with angular resolution of about 7 degrees. The resolution was limited, but the results were revolutionary. The COBE map showed the cosmic microwave background as a blotchy pattern of warmer and cooler regions, like colored spots painted on a cosmic sphere surrounding our position in the universe. The spots were the largest scale features of the primordial density field, variations that spanned significant fractions of the sky and represented the most ancient structures detectable in the cosmos. The image was fuzzy, but it was the first image of the early universe ever made. The detection of the temperature variations by COBE earned the Nobel Prize in Physics for John Mather and George Smoot in 2006. Recognition of the fundamental importance of confirming the primordial fluctuations that seeded all cosmic structure. Mather was honored for the spectrum measurement confirming the blackbody nature, while Smoot was honored for the detection of the anisotropies, revealing the primordial variations. Both results transformed cosmology. Following COBE, numerous ground-based and balloon-borne experiments improved measurements of the cosmic microwave background, probing smaller angular scales than COBE could resolve, and beginning to reveal the rich acoustic structure that would become a powerful cosmological probe. These experiments operated from high-altitude sites or from balloons in the upper atmosphere to minimize interference from water vapor that absorbs microwave radiation. Each experiment contributed pieces to the emerging picture. The WMAP satellite, the Wilkinson Microwave Anisotropy Probe, was launched in 2001 and operated until 2010, producing maps of the cosmic microwave background with angular resolution about 35 times better than COBE had achieved. The improved resolution revealed detailed structure in the temperature variations, showing the full pattern of primordial fluctuations across a wide range of angular scales. The picture of the early universe sharpened dramatically. WMAP measured the temperature of the cosmic microwave background in 5 frequency bands, allowing the cosmic signal to be separated from contaminating foreground emission produced by our own galaxy and other nearby sources that also produce microwave radiation. The separation of cosmic signal from local contamination is one of the major challenges in cosmic microwave background measurements, requiring observations at multiple frequencies where the different components have distinct spectral signatures. The WMAP maps showed the cosmic microwave background as a complex pattern of hot and cold spots at many different angular scales, from features spanning tens of degrees to features only fractions of a degree across. The distribution of power among these different scales, how much variation exists at each angular scale, became the primary observable for extracting cosmological information. The statistical analysis of this distribution yielded precise values for fundamental parameters. The Planck satellite, launched by the European Space Agency in 2009, carried instruments even more sensitive than WMAP and observed in 9 frequency bands spanning a broader range than previous missions. Planck operated until 2013, producing the most detailed all-sky maps of the cosmic microwave background ever made and the most precise measurements of cosmological parameters derived from this radiation. The Planck maps remain the definitive images. The Planck maps show the cosmic microwave background in stunning detail, with hundreds of thousands of individual features visible across the microwave sky. The pattern appears almost random, but contains statistical regularities that reveal the physics of the early universe with extraordinary precision. Colors on the maps indicate temperatures very slightly above or below the cosmic average. Differences so small they can only be seen by exaggerating the color scale enormously. The resolution of Planck was sufficient to see features only about 5 arc minutes across, roughly 1/6 the apparent diameter of the full moon as seen from Earth. This fine resolution revealed the detailed structure of the primordial fluctuations and allowed extraction of information that had been averaged out in the lower resolution maps from earlier missions. The improvement from Kobe to Planck spans more than 2 orders of magnitude in angular resolution. The frequency coverage of Planck was essential for separating the cosmic signal from various foreground sources, including emission from dust in our own galaxy, free radiation from ionized gas, and synchrotron radiation from electrons spiraling in magnetic fields. Each of these foregrounds has a different spectrum, allowing separation when observations are made at multiple frequencies spanning a broad range. The cosmic microwave background emerges after subtracting these contaminants. The Planck results included not only maps of the temperature variations, but also maps of polarization, the slight alignment of the electric field oscillations in the cosmic microwave background photons that encodes additional information about conditions in the early universe. Polarization measurements are more challenging than temperature measurements, but contain complementary information that helps break degeneracies between different cosmological parameters. The progression from Kobe through WMAP to Planck represents a maturing of cosmic microwave background cosmology, from detection through characterization to precision science, with each generation building on the foundation established by its predecessors. Future missions are planned that will improve further on Planck's measurements, probing even smaller angular scales and measuring polarization with even greater sensitivity to extract remaining information from this ancient radiation. The maps produced by these missions have become iconic images in astronomy, instantly recognizable representations of the early universe that have appeared in textbooks, popular science articles, and discussions of cosmology around the world. The colorful ovals showing the microwave sky have become the face of cosmology, visual symbols of the baby universe before any of the familiar structures we observe today had formed. The data from these missions continues to be analyzed and reanalyzed, with new techniques extracting additional information and checking previous results against improved methods. The raw measurements have been preserved and made publicly available, allowing researchers worldwide to contribute to the interpretation and to search for subtle signals that might have been overlooked in initial analyses. The scientific harvest continues. The patterns observed in the cosmic microwave background contain information about the universe as a whole, its geometry, its composition, its age, and the processes that shaped its early history before any structures formed. Reading this information requires understanding how the physical conditions in the early universe produced the specific pattern of variations that we observe. Connecting theory to observation through detailed modeling of the primordial plasma and its evolution, the cosmic microwave background has become a precision tool for cosmology. The angular scale of the variations, how large the spots appear on the sky, tells us about the geometry of the universe, whether space is flat like a tabletop, positively curved like the surface of a sphere, or negatively curved like a saddle shape. The characteristic size of the spots depends on how far sound waves could travel in the early plasma before recombination froze the pattern in place. And this distance appears at different angular scales depending on how light travels through curved or flat space. The measurements indicate that the universe is flat. Flat geometry means that the rules of ordinary Euclidean geometry apply on cosmic scales, with parallel lines remaining parallel forever, the angles of triangles summing to exactly 180 degrees, and the simple relationships of everyday geometry holding true across billions of light years. This flatness is actually remarkable, requiring the total energy content of the universe to be balanced with extraordinary precision against the rate of cosmic expansion. The flatness poses a puzzle that inflation helps explain. The composition of the universe can also be determined from the cosmic microwave background. By measuring the relative heights of peaks in the statistical description of the variations at different angular scales, the amount of ordinary matter made of protons and neutrons, the amount of dark matter that interacts gravitationally but not electromagnetically, and the amount of dark energy that drives accelerating expansion all leave distinct signatures in the pattern. The measurements constrain each component. The results indicate that ordinary matter, the protons and neutrons and electrons that make up everything familiar, constitutes only about 5% of the total energy content of the universe. Dark matter, whose nature remains unknown but whose gravitational effects are observed, makes up about 27%. Dark energy, the mysterious component driving cosmic acceleration, accounts for the remaining 68%. The universe is mostly dark. The age of the universe can be calculated from cosmic microwave background measurements by determining the rate of expansion and running the cosmic clock backwards to find when the expansion began. The result is approximately 13.8 billion years, with an uncertainty of only about 1% thanks to the precision of the measurements. This age is consistent with other methods of dating the cosmos, confirming the overall picture of cosmic history derived from many independent observations. The statistical analysis of the cosmic microwave background involves calculating what is called the power spectrum, a mathematical description of how much variation exists at each angular scale, from the largest features spanning the whole sky down to the smallest features the instruments can resolve. The power spectrum shows a series of peaks and troughs at different scales, each peak corresponding to a specific mode of oscillation in the early plasma. The pattern of peaks constrains cosmological parameters. The first peak in the power spectrum occurs at an angular scale of about 1 degree, corresponding to the size of regions that had just completed one compression when recombination occurred and the pattern froze. This peak is sensitive to the geometry of the universe, appearing at different angles depending on whether space is flat or curved. The observation that the first peak falls at almost exactly 1 degree confirms that the universe is flat. Subsequent peaks occur at smaller angular scales, corresponding to regions that had completed additional oscillations before recombination. The heights of these peaks relative to each other depend on the ratio of ordinary matter to dark matter, since the two components respond differently to the oscillating pressure waves in the early plasma. Ordinary matter is pushed around by the radiation pressure, while dark matter feels only gravity. The comparison between odd-numbered peaks and even-numbered peaks is particularly sensitive to the amount of ordinary matter, since the odd peaks correspond to compressions where matter and radiation were pushed together, while even peaks correspond to rarefactions where they were stretched apart. The relative heights reveal the matter content with remarkable precision, consistent with independent estimates from the abundances of light elements produced in the first few minutes after the Big Bang. The detailed shape of the power spectrum also reveals the spectral index, a number that describes whether the primordial fluctuations had equal power at all scales, or whether some scales were enhanced relative to others. Inflation predicts a specific value for this index, slightly less than 1, corresponding to slightly more power at large scales than at small scales. The measurements confirm this prediction, supporting the inflationary picture of the early universe. The polarization of the cosmic microwave background contains additional information beyond what the temperature variations reveal, including potential signatures of gravitational waves produced during inflation that would leave a distinctive pattern called B modes in the polarization signal. The search for this signal is an active area of research, with experiments attempting to detect the faint imprint of primordial gravitational waves in the polarized light from the early universe. The extraction of cosmological parameters from cosmic microwave background data involves comparing the observed power spectrum to theoretical predictions from models with different parameter values, finding the combination of parameters that best reproduces the observations. This process requires sophisticated statistical methods and careful treatment of uncertainties in both the measurements and the theoretical models. The results have become extraordinarily precise. The cosmic microwave background has transformed cosmology from a field of rough estimates and order of magnitude calculations into a precision science where fundamental parameters are measured to percent level. Accuracy, the age of the universe, the composition of matter and energy, the geometry of space, and other properties are now determined with confidence that was unimaginable when the radiation was first discovered accidentally in 1965. The ancient light has told us the vital statistics of the cosmos. The early universe contained sound waves, actual acoustic oscillations propagating through the primordial plasma like sound through air, and these waves left their imprint on the cosmic microwave background in patterns that we can still observe today. The concept of cosmic sound waves may seem strange, since we normally think of sound as requiring a medium like air or water to propagate. But the hot plasma of the early universe was exactly such a medium, capable of carrying pressure waves that traveled at remarkable speeds across cosmic distances. Sound, in the early universe, traveled at approximately half the speed of light, far faster than sound in any ordinary material, because the pressure was provided primarily by the radiation that filled the plasma, rather than by the matter itself. The radiation exerted pressure when compressed, pushing back against whatever squeezed it, and creating the restoring force that allowed waves to propagate. The speed of sound was determined by the ratio of pressure to density in this radiation-dominated plasma. These sound waves had been oscillating since very early times, triggered by the primordial density variations that were themselves produced during inflation in the first fraction of a second after the universe began. Each overdense region began collapsing under gravity, but the collapse was resisted by the pressure of the radiation, causing the region to bounce back and begin oscillating between compression and expansion. The oscillations continued until recombination froze the pattern. The waves traveled for the 380,000 years between when they were triggered and when recombination released the light that carries their record to us today. During this time, the sound waves crossed significant distances, with the fundamental mode traveling about 450,000 light-years before the oscillations froze. This distance corresponds to an angular scale of about 1 degree on the sky, as seen from our position today. When recombination occurred, the oscillations stopped because the conditions that allowed sound to propagate, the tight coupling between matter and radiation, ceased when the plasma became neutral atoms. The pattern of compressions and rarefactions at that moment was frozen in place, preserved in the density distribution of matter and in the temperature of the radiation that we observe today. The cosmic microwave background is a snapshot of the sound waves at the moment they froze. The regions that happened to be in the compressed phase when recombination occurred appear slightly warmer in the cosmic microwave background, while regions in the rarefied phase appear slightly cooler. This temperature difference arises from the gravitational effects of the density variations, with photons losing energy as they climb out of the denser regions. The pattern of hot and cold spots traces the frozen sound waves. The characteristic scale of these sound waves, the distance sound could travel before recombination, creates a distinctive feature in the cosmic microwave background called the acoustic peak. This peak appears in the power spectrum at an angular scale of about 1 degree, corresponding to regions that were maximally compressed at the moment the oscillations stopped. The peak is the most prominent feature in the power spectrum. Additional peaks appear at smaller angular scales, corresponding to higher harmonics of the fundamental oscillation. The second peak corresponds to regions that had completed a full oscillation, going through compression and rarefaction, and back to compression. The third peak corresponds to regions that had completed 1.5 oscillations, and so on. The series of peaks creates a distinctive pattern in the power spectrum. The relative heights of these peaks encode information about the composition of the universe, since ordinary matter and dark matter respond differently to the oscillations. Ordinary matter, tightly coupled to the radiation through electromagnetic forces, participates fully in the oscillations. Dark matter, interacting only gravitationally, does not feel the radiation pressure and begins falling into gravitational wells, even while ordinary matter is being pushed around by the oscillations. The presence of dark matter enhances the odd-numbered peaks relative to the even-numbered peaks, because dark matter deepens the gravitational wells into which ordinary matter falls during compression phases. This effect is observable in the cosmic microwave background power spectrum, providing independent confirmation of dark matter's existence beyond the evidence from galaxy rotation curves and other observations. The ancient sound waves reveal the dark matter. The same sound waves that are visible in the cosmic microwave background also left their mark on the distribution of galaxies that formed billions of years later, from the matter that carried the frozen oscillation pattern. This correspondence is called baryon acoustic oscillations, and it appears as a slight preference for galaxies to be separated by a particular distance corresponding to the sound horizon at recombination. The ancient sound echoes in the modern galaxy distribution. The detection of baryon acoustic oscillations in galaxy surveys confirmed the picture of sound waves in the early universe derived from the cosmic microwave background, providing independent evidence from a completely different type of observation. The same physical scale appears in both the microwave background and the galaxy distribution, scaled up by the expansion of the universe since recombination. The agreement is a powerful confirmation of the cosmological model. The sound waves of the early universe can be thought of as the cosmos ringing like a bell, with the primordial density variations serving as the initial strike that set the oscillations in motion. The ringing continued for hundreds of thousands of years, with different modes oscillating at different frequencies depending on their size. When recombination occurred, the bell suddenly stopped, its vibration pattern frozen in place for future observers to detect. The analogy to a musical instrument is apt, with the different peaks in the power spectrum corresponding to the fundamental tone and the overtones of a vibrating system. The relative strengths of these tones depend on the properties of the instrument, and by analyzing the cosmic sound, we can determine the properties of the cosmic instrument, the universe itself. The ancient music plays on in the patterns of the cosmic microwave background. The frozen sound waves of the early universe represent one of the most remarkable connections between physics at very different scales and times, linking quantum fluctuations in the first moment to acoustic oscillations over hundreds of thousands of years, to the distribution of galaxies billions of years later. The coherence of this picture, confirmed by multiple independent observations, gives confidence that we understand the basic physics of cosmic evolution from its earliest observable moments to the present day. The uniformity of the cosmic microwave background presents a puzzle that has guided cosmological thinking for decades. A question about how different parts of the sky can have the same temperature when they were never in contact during the early history of the universe. This puzzle, called the horizon problem, points toward physics operating in the very earliest moments of cosmic history, before the processes we have discussed so far could have shaped the universe we observe. The uniformity requires explanation. The cosmic microwave background has the same temperature in every direction to extraordinary precision, differing by less than 1 part in 100,000 from one region of the sky to another. This uniformity tells us that the early universe was extraordinarily smooth, with matter and radiation distributed almost perfectly evenly throughout the cosmic volume. But this smoothness is puzzling when we consider how information travels across the universe. Information cannot travel faster than light, and in the early universe, light had limited time to travel between different regions before recombination occurred and the cosmic microwave background was released. When we look at opposite sides of the sky, we see regions that were about 80 million light-years apart at the time of recombination, but light had only 380,000 years to travel between them. They were too far apart to have exchanged any signals. Regions that cannot exchange signals are said to be outside each other's horizons, causally disconnected in the language of physics. The horizon at recombination was much smaller than the separation between opposite sides of the cosmic microwave background sky. meaning that different regions of the sky should have evolved independently without any communication between them. Yet, they all arrived at the same temperature, as if they had coordinated somehow. If different regions evolved independently, there is no obvious reason why they should have reached identical temperatures. Temperatures equilibrate through the exchange of energy, but energy cannot be exchanged between regions that are outside each other's horizons. The uniformity we observe seems to require that something connected these regions before the horizon could catch up with their separation. Something established equilibrium before the normal causal processes had time to operate. This puzzle is the horizon problem, and it suggests that the simple picture of cosmic expansion from the earliest moments is missing something important about the very beginning. The universe appears to have been prepared in a special state of near-perfect uniformity, but the processes that would normally establish such uniformity had not had time to operate, given the finite age and the finite speed of light. The leading explanation for the horizon problem is cosmic inflation, a period of extremely rapid expansion that occurred in the first tiny fraction of a second after the universe began. During inflation, the universe expanded by an enormous factor in an almost inconceivably brief time, far faster than the speed of light would normally allow information to travel. This rapid expansion stretched a tiny region, small enough to be in causal contact, to encompass the entire observable universe. Before inflation, the region that would become our observable universe was small enough that light could have crossed it many times, allowing temperature and density to equilibrate throughout the volume. Inflation then stretched this equilibrated region to cosmic scales, carrying the uniformity established on small scales to the much larger scales we observe in the cosmic microwave background today. The uniformity is a fossil of pre-inflationary equilibrium. Inflation also explains the flatness of the universe, another puzzle that emerges from careful consideration of cosmic dynamics. Flatness requires an extraordinarily precise balance between the energy content and the expansion rate, a balance that would seem to require fine-tuning of initial conditions to achieve. Inflation naturally produces flatness by stretching any initial curvature to unobservable levels, just as inflating a balloon makes a small region of its surface appear flat. The primordial fluctuations that seeded all cosmic structure also have a natural explanation in inflation, as quantum fluctuations in the very fabric of space were stretched to cosmic scales during the rapid expansion. These fluctuations, normally invisible at microscopic scales, became the density variations that eventually grew into galaxies and the cosmic web. The quantum became cosmic through the stretching of inflation. The temperature variations in the cosmic microwave background preserve the statistical properties of these inflationary fluctuations, allowing observational tests of the inflationary hypothesis through careful measurement of the primordial power spectrum. The observations are consistent with the predictions of simple inflationary models, supporting the basic picture while leaving room for more detailed investigations of exactly what physics drove the rapid expansion. The horizon problem and its inflationary solution connect the cosmic microwave background to the very earliest moments of cosmic history, far earlier than the recombination epoch that directly produced the radiation we observe. The uniformity of the background tells us that something special happened in the first moments, something that established the conditions from which the subsequent evolution proceeded. The physics of inflation remains an active area of research, with many different models proposed that all share the common feature of rapid early expansion, but differ in their detailed predictions for observable consequences. The cosmic microwave background provides constraints on these models, ruling out some possibilities while leaving others viable. The ancient light carries information about moments far earlier than its own release. The uniformity that puzzled cosmologists has become evidence for physics operating at energy scales far beyond anything accessible in laboratory experiments. The physics of the universe's first moments, when expansion was driven by processes we are still working to understand. The horizon problem is not just a puzzle, but a window into the very beginning. A clue that the cosmic microwave background carries about events preceding its own formation. The puzzle of uniformity and its inflationary resolution represent one of the great conceptual advances in cosmology, connecting observations of the present-day universe to physics operating at the earliest times. The ancient light we observe tonight preserves information not just about recombination, but about the conditions established before recombination, conditions that required special physics to achieve, and that shape everything we observe today. The cosmic microwave background continues to arrive from every direction tonight. Ancient photons, completing journeys that began when the universe was young and unfamiliar, before any of the structures we know had formed from the primordial smoothness. The light has been patient, traveling at the maximum possible speed, yet requiring billions of years to cross the expanding cosmos, carrying information about conditions that existed long before any planet or star or galaxy emerged from the density variations it preserves. The radiation fills all of space uniformly, surrounding everything in a faint glow that is invisible to human eyes but detectable with appropriate instruments that can sense microwave wavelengths. This glow permeates the universe, passing through galaxies and the spaces between them equally, the most pervasive phenomenon in the cosmos, and the oldest electromagnetic radiation accessible to observation. Everything we can see or detect exists within this bath of ancient light. The light arriving tonight is not the same light that arrived last night, though it comes from the same epoch and carries the same information about the early universe. Each moment brings photons from slightly different directions, slightly different regions of the surface of last scattering, all telling the same story of a hot, smooth universe cooling and clearing to release the radiation we observe. The message continues arriving, moment by moment, photon by photon. Tomorrow will bring light from regions slightly farther away, photons that are currently still traveling through the final stages of their journey toward Earth. In a million years, light from correspondingly more distant regions will arrive, though it will look essentially identical because the universe was essentially identical everywhere at the moment of last scattering. The message is the same from every direction. The signature of cosmic uniformity at the earliest observable epoch. The cosmic microwave background has transformed our understanding of cosmology, providing a window into the early universe that no other observation can match. Before its discovery, cosmology was largely a theoretical enterprise, with limited observational constraints on models of cosmic history. After its discovery and detailed measurement, cosmology became a precision science, with fundamental parameters determined to percent-level accuracy from patterns in this ancient light. The things we have learned from the cosmic microwave background include the age of the universe, approximately 13.8 billion years from the moment of beginning to the present day. The composition, with ordinary matter making up only 5%, while dark matter and dark energy dominate the cosmic energy budget. The geometry, flat to remarkable precision. The initial conditions, nearly scale-invariant fluctuations consistent with an inflationary origin. Each measurement has confirmed and refined the standard cosmological model. The things we have yet to learn from the cosmic microwave background may be equally profound, including, potentially, the signature of primordial gravitational waves produced during inflation that would leave a distinctive pattern in the polarization of the radiation. Experiments are actively searching for this signal, which would provide direct evidence for inflation and information about the energy scale at which it occurred. The ancient light may still have secrets to reveal. The future of the cosmic microwave background itself extends far into the cosmic future, though the radiation will continue cooling as the universe continues expanding. In 1 trillion years, the temperature will be thousands of times lower than it is today. The wavelength stretched far into the radio portion of the spectrum, where detection would become increasingly challenging. The glow will fade, but will not disappear, cooling toward absolute zero, but never quite reaching it. The instruments that have mapped this radiation, from the Horn antenna in New Jersey to the sophisticated satellites orbiting far from Earth, represent human curiosity manifested in technology capable of detecting the faintest signals nature provides. The same species that once looked up at the stars with naked eyes has built machines that can measure temperature variations of 30 millionths of a degree across the sky, extracting information from photons that have traveled for 13 billion years. The scientists who have dedicated careers to measuring and interpreting this ancient light have contributed to one of the great achievements of human knowledge: the understanding of cosmic history from its earliest observable moments to the present day, from Penzias and Wilson's accidental discovery to the precision cosmology enabled by satellite missions. Generations of researchers have built an understanding of the universe that rests substantially on this single phenomenon. The cosmic microwave background connects us to the earliest epoch of cosmic history that we can observe directly, a time before atoms, before stars, before galaxies, before anything familiar except the physics that continues to govern the universe today. The light carries a message from this ancient time, telling us what the universe was like when it was less than 500,000 years old, an infant cosmos that would grow into the structured universe we inhabit. The light that fills space tonight has been traveling since long before Earth existed, before the Sun formed, before the Milky Way assembled from smaller precursors. The light will continue traveling long after we are gone, passing through whatever the universe becomes in the cosmic future, carrying its message to any detectors that might be built to receive it. The journey continues. The oldest light in the universe still arrives, moment by moment, filling space with the echo of creation. The ancient glow surrounds us always, invisible but present, cold but carrying the memory of heat, uniform but encoding the seeds of all structure. 13 billion years after its journey began, the light is still arriving, patient and persistent. The oldest thing we can observe, still telling its story to anyone who builds instruments to listen. The cosmic microwave background will continue arriving through the night, through all nights, through cosmic time beyond any scale we can meaningfully comprehend. The radiation that has already been traveling for 13 billion years will travel for billions more, stretching and cooling but never ceasing, filling the universe with the remnant of its hot beginning. The oldest light continues its journey, and we are fortunate to live in a time when we can detect it and understand what it tells us about the cosmos we call home.